In this section we will talk about dynamics of rotational motion and equilibrium of rigid bodies. So far we have learned about motion of objects and its relation to Newton's laws. We learned that forces interacting with an object can change its behavior in terms of its speed and direction. But we have not yet dived deep into objects that are rotating, and we regard them like pulley systems as frictionless. In reality they do contribute to the value of the physical quantity that describes the phenomenon. So let us begin discussing them. Torque is defined as the quantitative measure of the tendency of a force to cause or change the rotational motion of a body. In general, tau or torque is equal to the cross product of the displacement r times the force. As shown in the figure, the displacement r is the point where the force interacts, and we can deduce that this force will cause a rotational motion when we fix the bar at point P to allow it to rotate at that axis. We take a brief review about a mathematical method called the cross product. Let's say you have two vectors A and B. Find the cross product A cross B. The product is given by C equals A cross B as shown in the figure below. So vectors A and B lie on the same plane or flat surface. To determine the direction of C or the cross product, we use the right-hand rule, where the direction of B is indicated by the palm where it crosses by curling it to the direction of B. The direction of the thumb points the direction of vector C. Note that the vector C is perpendicular to vectors A and B. Another way of looking at it, we have the screw image where the flat tip of the screw lies on the surface of the vectors A and B, and when you turn the screw counterclockwise it provides the direction of curling from B to A. The direction of the tip or the pointy part of the screw points the direction of vector C. Like the dot product where we can get its magnitude, we can also obtain the magnitude of the cross product. The cross product is given by the function the magnitude of A and B times sine function of the separation angle phi between A and B. Now we are equipped to determine the mathematical formulation for the physical quantity torque. To determine the magnitude of the torque, we apply the mathematical method earlier. So, the torque is equal to the magnitude of the displacement r from the point of rotation to the point where the force is interacting times the magnitude of the force times the sine function of theta, or the angle between the force times. The direction of the torque is given by applying the right-hand rule. So the base of the palm moves in the same direction as the force, then curls towards the displacement. So we see that the direction of the torque is going outwards, the surface indicated by the dot symbol. The torque equation can be simplified as force times moment r_ml. We can examine the value of torque for three general positions of force acting on the same object. First position A. The torque is a positive torque, which is an indicator that the rotation is counterclockwise and its direction is outside of the page as shown in the previous slide using the right-hand rule. Second position B. The position of the force causes the body to rotate the body in a clockwise manner. So, we add a negative sign and the torque is directed inward of the page. The last position is directed on the point of rotation, which will not cause the body to rotate in any direction. Now we examine torque for an arbitrary shaped object or rigid body where three forces are placed at different positions. For position A, the torque is a positive torque, which is an indicator that the rotation is counterclockwise and that its direction is outside of the page as shown in the previous slide using the right-hand rule. Second position B, the position of the force causes the body to rotate the body in a clockwise manner. So, we add a negative sign and the torque is directed inward of the page. The last position is directed on the point of rotation, which will not cause the body to rotate in any direction. Here note the term line of action, which simply suggests the direction of the force intersecting also the point of rotation. The vector L or moment replaces the vector r, which the symbol L represents the moment lever arm. Torque and angular acceleration for a rigid body. Consider again a rigid body to be made up of a large number of particles. Choose the first particle m1 as shown in the figure. Consider that particle in red as mass 1 and rotates at an axis or y-axis as the rest of the particles having the same motion as mass 1. We take that the force tangential on this mass is given as mass 1 times acceleration of mass 1. If we recall what we learned from the equations of motion for rotational motion, we have that the tangential acceleration is equal to the radius or distance from the axis of rotation to the position of mass 1 times the angular acceleration. Then we have the force 1 tangential is equal to the r1 times alpha, which we then multiply by r1 on both sides and get an expression shown in red. From the equation we obtained earlier, we see that the mass times the r squared is equal to the moment of inertia of that mass. Also the r times f, where the angle between them is 90 degrees, which the sine of 90 equals to 1 is equal to tau or torque formulation. So we can rewrite the expression earlier as a function of moment of inertia, or torque is equal moment of inertia times angular acceleration for mass 1. The other force 1y and F1 radial does not contribute to the total torque. So for multiple masses we simply take the sum of the individual torques for each mass, which is also equal to the moment of inertia times the angular acceleration. This means that the sum of torques acting on the body is proportional to its angular acceleration. This equation is the rotational analog of Newton's second law, or F equals ma. In the previous sections we learned that when the body is at rest, the forces acting on it must cancel each other so that the net force will be zero, which we will call the first condition. However, bodies can have zero sum of net forces but still moving with respect to its axis, or in other words stationary but rotating. So, to have a completely at rest or in equilibrium, we note a second condition, which is the net torque is also zero. Now, if both cases are satisfied, a body is at rest kinematically and rotationally as shown in the figure. Here we have an example. A sign of mass 20 kg hangs from the end of a rod of length 2 meters with a mass of 4 kg. A wire attached to the end of the rod and to a point 1 meter above point O. Find the tension in the wire and the force exerted by the wall. First step is to draw an FBD. Here we see the present forces, which are the force F with its components Fx and Fy. Fx is the force exerted by the wall onto the rod. We also have the tension T and its components Tx and Ty. We also have the weights W1 for the rod, which has a mass of 4 kg, and weight 2, which has a mass of 20 kg. In the second step we sum the forces along its rotation and axis. So for the tension we apply the second condition for equilibrium to solve it. So we examine the figure and determine if that force would cause rotation clockwise, counterclockwise, or no motion at all given the axis of rotation at the origin O. So for the first one is the force F, which is located on the axis of rotation, which we learn that it will not cause in rotation if its line of action intersects the point of rotation. The second term is due to the weight 1, and if we let the rod move freely, this force will cause the body to rotate clockwise. The third is due to weight 2, which like weight 1 will cause the rod to rotate clockwise. And the fourth one is the tension T, and will cause the body to rotate counterclockwise. Then we expand the equations and see that the angles between the lengths R1 and R2 with the weights 1 and 2 is the same, which is 90 degrees. The sine function of 90 degrees would yield a value of unity, or 1. So we can simplify the equation for the tension as shown here. However, the angle theta is unknown and we need to find it first so that we can solve the value of t. To solve for the angle theta, we simply examine the figure and we see that it can be solved using the lengths that are present in the problem. By applying tangent function we can obtain the value of theta. So, theta is the inverse of tangent of the ratio of 1 meter over 2 meters, which yields a value of theta close to 26.6 degrees. We then substitute this value to the expression we got earlier and we see that the tension experienced by the wire holding the rod in equilibrium is around 483.6 newtons. To determine the force exerted by the wall we use the first equation of equilibrium, which simply is the sum of forces along its axis. We see that the forces along x are just the force x component of the wall minus the tension x of wire. Upon substitution of the values of t and theta we get that the force x, or the force exerted by the wall on the rod, is around 432.4 newtons. Here we continue to solve the problem, which is not necessary but interesting to do since we can determine the force y by the wall. We can then solve for the force F of the wall, which is oriented as shown in the figure. It is around 432.8 newtons and oriented in a non-linear fashion. Here we have a ladder whose length L is 12 meters and whose mass M is 45 kilograms rests against a wall. Its upper end is a distance h of 9.3 meters above the ground. The center of gravity of the ladder is 1/3 of the way up the ladder. A firefighter whose mass M is 72 kilograms climbs halfway up the ladder. Assume that the wall, but not the ground, is frictionless. What forces are exerted on the ladder by the wall and by the ground? First we draw an FBD for the system and we see the forces that are present. First is the force by the wall that is perpendicular to its surface, and we could say that this is also the normal force from that wall. The angle between this force and the ladder is theta, which is determined by symmetry or geometry. We note that this wall is smooth or frictionless, which suggests that there would be no force countering the slide along the wall or y-axis in this part. The next two are the weights, the weight by the person or firefighter and the weight of the ladder with an angle phi with respect to the ladder. The next one is the force exerted by the ground surface on the ladder at point O, which we could say is the normal force from this second surface. The last one is the friction force by the ground surface, which counters the slipping direction of the ladder, preventing it from moving. So the system is in equilibrium and we could use the conditions of equilibrium to solve for force exerted by the wall onto the ladder. The next step is that we use the second condition for equilibrium, which is that the net torque is equal to 0. Here we identify the forces that could cause the motion of the body to rotate clockwise and counterclockwise if it is allowed to move freely with respect to its axis of rotation positioned at point origin O. For the first force, or force exerted by the wall, it would cause the body to rotate clockwise. For the weights WP and WL, they would cause the body to rotate counterclockwise, and for the forces, the normal force and friction, whose line of action intersects the point of rotation, they both do not cause movement, so they are both 0. So we see that the function is simplified further and we rearrange it to obtain an expression for the force exerted by the wall. We see that we need to solve the angles or the sign of the angles to get the value of the force. To solve for the angles or sign of the angles, we go back to the figure and we see that the angles theta and phi form a right triangle, which we write about in terms of its sine function. First, for theta, it's simply sine theta is equal to h over L. For phi, it is sine phi is equal to a over L. So, we encounter another problem since a is an unknown and we need to get a better expression for it. Applying the Pythagorean theorem, we see that L squared is equal to A squared plus H squared. Solving for A is equal to the square root of L squared minus H squared. Substituting this to our sin phi function, we get that sin phi is equal to the square root of the difference of square of L and H over the quantity L. Now we can stop here and substitute these values, but we can also simplify the ratio of the sine functions that is present in the equation for force exerted by the wall. The sine ratio of phi over theta is done by substituting the values of the individual sine of each angle, and we get that it is equal to the square root of the difference of the squared L and G over the quantity H. We then substitute this back to expression for Fw. Substituting the obtained function from the ratio of sine phi over sine theta, we have now an equation that we can use to determine the value of Fw. We then substitute the values from the given, and we see that the force exerted by the wall is around 407 newtons. Here we have an object moving in both translational and rotational motion. So, we see the rigid body is moving around its axis, which is the center of mass of the object. At this point the rigid body rotates around it, and where the translational motion also points the direction of motion of the object, translation Li. Let us examine this motion further in the next slide. So, we dissect the behavior of this object. Here we see that there are three velocities that are involved here for the translational motion. We have the velocity along the center of mass denoted by Vcm, the tangential velocity which is denoted here by v' I for mass I, and the sum of these two vector velocities which is denoted as vi for mass I. Mathematically we can write an expression for the sum of the kinetic energy of these velocities as shown in the slide. We recall the expression for the kinetic energy, which is 1/2 of mass I times the square of the velocity of mass I. We substitute the velocity with its components, which are the velocity of the center of mass and the tangential velocity. We get an expression that is in the quadratic form as shown here. This equation is the kinetic energy for the mass I only, and the next step is to sum for all the masses inside the rigid body. To do that, we simply take the sum of kinetic energy, which is the individual sum of each three terms. So we see that the second term is 0, since the total mass m times the velocity of the center of mass relative to the center of mass is 0 by definition. Now we have a kinetic energy calculation that incorporates both translational and rotational motion of a body. This equation adds a much more adequate solution to problems that combines both motion with its adaptive formula that can tackle objects of different shapes. For a rigid body then, the sum of forces can be expressed by the sum of external forces and the net torque as shown in the slides. So when we have problems that involve rotation, such as the figure shown in the slide where the mass translation moves but it is connected to a pulley that is stationary but rotates about its axis, two conditions must be met for the utilization of the torque net. For the utilization as indicated by the explicit indication of the term moment of inertia about its center of mass is that letter A, the axis through the center of mass, must be an axis of symmetry, and letter B, the axis must not change direction. So the pulley in the figure satisfies both conditions. Here we have a disc pulley that has a radius r and mass m. The surface between mass m2 and the ramp is not frictionless with coefficient of kinetic friction. The mass m2 slides down to the left while mass m1 moves upward. For letter A, derive an expression for the acceleration of the masses. For letter B, find the tensions T1 and T2. First we draw the FBD for each mass. Here we have for mass 1, and we note there are no forces along the x-axis, so it is just two forces, tension and weight 1. The second mass lies on a plane with friction and the block moves downward with acceleration A. Here the tension is labeled as T2 to differentiate from T1 earlier. Here we have considered that the tensions are different or T1 is not the same as T2. Here we add an FBD for the pulley that relates the two masses through their tensions. So the pulley is a disk and it is allowed to rotate with an angular acceleration. Here we will assume the pulley as a disk with a moment of inertia. The next step is the summation of forces. We sum forces along the y-axis and we get that the tension 1 is equal to mass 1 times gravitational acceleration plus mass 1 times acceleration a. Next we sum the forces for mass 2. For the x-axis we have a negative tension, a negative friction and a positive weight component along x equals to mass times acceleration. We write an expression for tension 2 which is equal to the weight times sine theta minus the coefficient of friction times the normal force minus mass 2 times acceleration. To get an expression for the normal force we use the sum of forces along the y-axis which we then substitute to the previous equation. So, the expression for the tension is simplified further as shown in equation B. For the pulley system, we use the sum of torque or net torque which is equal to the moment of inertia times angular acceleration. So we have two forces and we examine which one causes the rotation clockwise and counterclockwise. So for tension 1 it can cause the disk to rotate counterclockwise so it has a positive sign. For tension 2 it can cause the pulley to rotate clockwise so it has a negative sign to indicate its direction of motion. Here the disk is assumed to have the same moment of inertia at its center of mass as a solid cylinder which is equal to 1/2 times the mass times the radius. We also recall the expression of angular acceleration in relation to translational acceleration, or to be more specific the tangential acceleration, as equal to the fraction of acceleration over the radius r. Substituting these equations we obtain equation D. We then use this expression and substitute the other two expressions of tension. Substituting the equations for the tension or equation A and B to equation D to get an expression for the acceleration. So, here we have a couple of steps to simplify equation D, so double check as you transpose terms, especially the signs. Written in at the bottom is the expression for the acceleration A. To determine the tension 1, we substitute the expression of acceleration obtained in the previous slides or equation E to equation A. So we simplify this expression of tension 1 as shown here. Similarly, to determine the tension 2 we also substitute the expression of acceleration obtained in the previous slides or equation E to equation B. So we simplify this expression of tension 2 as shown here. Both equations for the tensions are quite long, so it is important to double check your expressions and make sure that the terms contain all that is given in the problem. Now let us look at work and power produced in rotational motion. In rotational motion, we can express work in terms of torque and angular displacement. The work or derivative of work by the force while a point on the rim moves a distance derivative s is given by the expression dW equals F tangential times derivative of s. Recall that ds here represents a derivative of the arc, so we can have the expression for the ds as equal to the radius times d theta, which we substitute to the equation of work and get the formula for derivative of work as a function of torque times d theta. Now to sum all over this derivative of work we integrate it over a range of theta 1 to theta 2. So we get that the work is equal to the torque times the change in theta. We can further express work in terms of moment of inertia by using the relationship between torque and moment as torque equals to moment of inertia times angular acceleration. Substituting this to the derivative of work expression which and integrating it over the range angular velocity 1 to angular velocity 2, we get the expression of work as 1/2 times moment of inertia times the square of the change of angular acceleration. So we have two expressions of work as a function of torque or moment of inertia. To get the expression for the power expression, we recall the equation for power, which is the change of work over the change in time. Substituting the work expression in terms of torque, we get a value containing the ratio of change in theta over change in time, which is just the angular velocity. So, power is equal to torque times angular velocity. In this example, we have a flywheel of an engine that has a moment of inertia 2.50 kg/m2 about its rotation axis. For letter A, find the constant torque that is required to bring it up to an angular speed of 400 rev/min in 8.0 s, starting from rest. For letter B, we are asked to find the final kinetic energy. First we recall the expression of torque, which is equal to the moment of inertia times the angular acceleration, and the expression for angular acceleration, which is equal to the change of angular velocity over the change of time. Substituting the expression for the angular velocity to the torque equation, we get that the value for the torque is around 13.1 Newton meters. Note that we have first converted the angular velocity from revolution per minute to radians per minute so that we can find units that are appropriate for torque values. To determine the kinetic energy, we recall the expression of work total for rotating bodies. This work is contributed by the kinetic energy due to the motion of the body. So we substitute the given values and we see that the kinetic energy of the body is around 52 joules. Angular momentum is analogous to the linear momentum in the translational motion. Angular momentum is the cross product of the radial length cross with the linear momentum p. So we get an expression containing r times sine phi, which is what we call the lever arm as shown earlier. So, the angular momentum is an expression equal to mass times velocity times the lever arm. Here we want to relate the angular momentum to the moment of inertia. Now we consider a rigid body rotating about the z-axis with an angular velocity. Here a representative mass mi is positioned a distance ri from the center of origin or center of rotation with a velocity vi. The velocity of mass I is equal to Vi equals to Ri times angular velocity. Recall that the expression for the angular momentum is a cross product of r and linear momentum p, which means that the direction of angular momentum perpendicular to the plane of Ri and Vi. So, that means that the direction of angular momentum is along the positive z-axis as shown in the figure. Mathematically we substitute the expression of the Vi, and the angle between Ri and Vi is phi equals to 90 degrees, so it would yield a sine 90 degrees equal to 1. So we get that the expression we are left with is that Li is equal to mi times square of Ri n times angular velocity, which we can simplify as the moment of inertia times angular velocity. Here we want to relate the change in angular momentum to torque and its implication. So if we take the derivative of a cross product, which is the cross of each term, in a different way, which we will see here. So we take first the derivative of the first term r times the mv or momentum, then plus the r cross with m times the derivative of v with respect to time. We simplify this as v cross with mass times v plus r cross m times angular acceleration. Since the v cross with v will yield a sine function of theta equals 0 to 0, then the first term is cancelled. So, we are left with the derivative of angular momentum with respect to time as r cross with mass times acceleration, or simply cross with force. We see that the value obtained is just the expression for the torque. The implication for this is that the rate of change of angular momentum is equal to the torque of the net force acting on the rigid body. Now considering the condition for a rigid body rotating, the sum of the total torque is given as the derivative of angular momentum L with respect to time. If the net torque is 0, the derivative of L with respect to time is 0. This implies that the angular momentum is constant or conserved. So that means that if the body has been rotating, it would continue to rotate unless acted upon by an external force. This is similar to Newton's first law of motion or law of inertia. So, just like a spinning top, it will remain spinning with a net rho k0 unless friction or change in surface or an external force acts on it. In addition to what we learned, we will talk briefly about center of gravity and its relation to center of mass. The gravitational torque about any point can be found by assuming that all weight of the body acts at its center of gravity, cg, which is identical to its center of mass, cm, if it is the same at all points on the body. So for a uniformly distributed mass spread across a rigid body or constant density at all volumes, then the center of mass is equivalent to center of gravity. Then to determine it, we simply use the formula used to find center of mass for center of gravity, which is the sum of the individual masses times their corresponding position on a certain axis. The end for now, and I hope you learned something new today. For questions and comments, you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at diys@diyslearningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next meeting.